So I am Vinny from Atlantic Woodworks, and this is the day 2 of the fire safety webinar series with Stephen Kraft. And today we're going to be talking about the fire safe design of the modern mass timber buildings with Steve Kraft. A little profile of Steve here. Dr. Stephen Kraft is a founding partner of the CHM Fire Consultants and has been applying his expertise in fire safety and wood construction to building design and research over the last 10 years. Previously, he served as an adjunct professor in the fire safety engineering program at the Carleton University from 2010 to 2019, and was a research scientist with Canada's National Forest Product Research Institute, FP Innovations, from 2006 to 2011. He was an undergraduate degree in forest engineering from the University of New Brunswick and a PhD in fire safety engineer from Carleton University. He is active in codes and standard development. If you're ready, Steve, you can start.
Great, thank you, Vinny. Welcome, everyone. So this afternoon, we're going to be talking about fire performance of mass timber, and I'm really excited to be speaking on this topic today. This has really been an area of work for me for the last probably 15 years or so, first in research and then for the last 10 years or so in design. So I would say that mass timber, the mass timber projects that we work on are certainly our most interesting and fun projects to work on. So I'm really happy to be talking about this today. I will plan for about a 50-minute presentation, and then at the end of that, I'll leave time for questions. So if you have any questions throughout, just save them till the end, and I think you can either put them in the chat or perhaps ask them at the end. So with that, Vinny gave a overview or a bio on me, so I won't go into this. My email is on this slide if anybody wants to get a hold of me after. So the presentation today, we'll talk a little bit about building code and National Building Code of Canada, specifically on alternative solutions and how there's two ways to satisfy the code, the building code, and a little bit, very briefly, on some of the changes that are taking place in the prescriptive requirements for mass timber buildings, and we'll go into that in a little bit of detail. And then I'll speak a little bit about alternative solutions and give a couple examples. And then we'll look a little bit at the research, specifically some of the latest research. And that will lead us into some discussion on some demonstration fire tests that some small scale ones that have taken place recently and some large scale ones that are planned for next year. And we'll finish on that. So I'm sure many of you are familiar with mass timber and some of the benefits of building with mass timber. I included this slide just because there are many different benefits, and some of them are realized on some projects and others might be realized on other projects. So they don't necessarily apply to every project, but things like obviously sustainable construction and carbon sequestration and overall lower environmental impact. But then there's some practical aspects such as speed of construction due to the having components prefabbed, and so they show up on site and they're quickly put in place, and the building can go up very quickly. Other potential benefits like a lightweight structure if soil conditions are poor. Obviously, a mass timber building is going to be significantly lighter than a concrete building. One of the big aspects I would say is the design aesthetics. So when it comes to mass timber buildings, as opposed to concrete or steel, the structure is on display and is part of the interior finish. And certainly many mass timber buildings, that's a big part of it. And we'll see a couple examples of that today. And then there in some projects, there might be benefits to just the structural system, perhaps how it satisfies seismic performance or energy performance. And so those will be project specific. But that's just some of the reasons why so many developers and architects are looking at mass timber these days. So just real quickly, with respect to the National Building Code, there's two ways to satisfy the requirements in the building code. One is to comply with the acceptable solutions in Division B, and that's, for example, for fire and for larger buildings, that's Part 3 of the building code. And of course, most buildings are designed this way. It's certainly, when we're talking about average buildings, from a design perspective, it's very cost effective to follow the acceptable solutions in the code and basically follow it as a cookbook and basically design our building that way from a fire safety perspective. But there's another way to comply with the code, and that's using alternative solutions. And alternative solutions have to achieve at least the minimum level of performance required by the acceptable solutions in Division B, as defined by the objectives and functional statements. And so that's where many of these mass timber buildings come in, is through the alternative solution process. And we have to demonstrate that the building's as safe as what the code would require. So in many cases, when we're talking about taller mass timber buildings, that comes back to non-combustible construction. So with respect to the acceptable solutions, I thought I'd touch on the new construction type that's being added to the National Building Code in the next edition, which I believe is still on course to be published later this year or by the end of the year. And so everybody's aware that there's two construction types currently in the 2015 National Building Code. We have combustible construction and non-combustible construction. And so the next version will have a third type of construction called encapsulated mass timber construction. And in some places, this has already been adopted. So ahead of publication of the National Building Code, there's many municipalities in British Columbia that are currently following or allowing this new type of construction, as well as Alberta. And we'll touch on what those are in a second. So I'll also mention that there were changes to the National Fire Code to reflect this new type of construction, and some of the construction site fire safety requirements have been put into the National Fire Code for these taller mass timber buildings. So this new construction type, basically encapsulated mass timber construction, it's exactly as it sounds, and is that it's mass timber construction with a large amount of the structure itself is encapsulated. And we'll look at how much on the next slide. But these buildings can be up to 12 stories in tall, with a height limit of 42 meters between the first floor and the uppermost floor. So whether that's the 12th floor, or perhaps it's the 10th floor, or perhaps it's a mezzanine, whatever the uppermost floor level is of the building. So that 42 meters can be a little bit restrictive on a 12-story building. So it's something to keep in mind. Two primary occupancy types, Group C and Group D. So your residential or office or professional services. And the maximum building area, these are quite large buildings. So the building area, basically the footprint of the building for residential, is 6,000 meters squared. And for Group D or business, 7,200 meters squared. So these are quite large buildings, as you can appreciate. So some of the requirements for encapsulated mass timber construction, this new construction type. Mass timber, there are minimum sizes for mass timber. So in developing these code provisions, there's a recognition that the mass timber performs a certain way, or we expect it to perform a certain way, and that's largely because of the size of the mass timber. Because in a fire, it behaves differently than, say, light frame. And so based on that, there are minimum size requirements for the mass timber itself. These buildings are going to be 2 hours of for the fire rating for the floors, and of course supporting construction as required in the code. So basically what we would expect for a high-rise building. And then for the encapsulation, there's generic solutions as well as there's a performance-based solution. So the generic solution is 2 layers of 1/2-inch Type X gypsum board. So that would be on columns, on walls, on ceiling, basically on the mass timber. On the floor, there's the generic solutions, a 38mm thick gypsum concrete or concrete topping. So 1.5 inches of concrete on the floor. To deviate from these generic solutions, there is a new test method that was created under the ULC Fire Test Committee, KNULC S146. And basically it's looking that it prevents temperature rise of the mass timber to a certain point for 50 minutes. And the other requirement is that the encapsulation material be non-combustible. So things like mineral wool insulation could satisfy that, for example. So as the name suggests, encapsulated mass timber construction, the structure is largely encapsulated with typically gypsum board, but there are some exceptions allowing for some exposed mass timber in these buildings. Exposed beams and column area of less than or equal to 10% of the perimeter wall area. So that's a little bit, perhaps sounds a bit strange if you don't realize where these numbers have come from. And they've come from research tests where basically the amount of encapsulated or the amount of exposed mass timber has always been expressed as a percentage of the wall area. So that doesn't allow, 10% doesn't allow for all beams and columns to be exposed, and it is rather restrictive actually. So that's one of the reasons we see alternative solutions being proposed for these kinds of buildings, because architects would like to expose more than the 10%. Similarly, in projects that do have mass timber walls, I would say it's relatively rare, perhaps with the exception of exit stair shaft or elevator stair shaft walls. Generally, we don't see mass timber walls. But if there are walls, then up to 35% of the perimeter wall area can be exposed for mass timber walls. And ceilings, up to 10% of the ceiling can be exposed. So perhaps if it's a CLT floor assembly, the ceiling underneath, 10% of that CLT can be exposed. Or if there's no walls, 25% of that ceiling. We'll touch a little bit on where those numbers come from, but basically it was that came from research that was conducted early on, probably about 10 years ago. And we do have more recent information, and it's quite possible in the future we'll see these numbers relax a bit in allowing more mass timber to be exposed. So those are the new prescriptive requirements. And of course, the other way to comply with the code is through alternative solutions. And this is a case where certainly the majority of projects we see right now are following the alternative solution pathway for mass timber, as opposed to following even in many jurisdictions, the prescriptive requirements for encapsulated mass timber, while they aren't accepted yet, for example, for use in Ontario, it's generally recognized that if you follow that design philosophy, then it's a relatively simple alternative solution. But once we deviate from that, it becomes a bit more complex and we have to go back to research to demonstrate performance. So what I wanted to mention here is that, as we mentioned, the alternative solution has to achieve at least the minimum level of performance required by Division B in the areas defined by the objectives and functional statements attributed to the acceptable solution. So basically, if we know that a building is required by code by Division B to be non-combustible construction, then if we're going to develop an alternative solution using mass timber, we have to be able to demonstrate that the performance of that building using mass timber is as good or better than the non-combustible construction solution. And of course, we don't have a very fine scale to measure risk in a building, whether it's risk to occupants, whether it's risk to the fire service, or whether it's risk to property damage. We don't have a fine scale for that. And so what we tend to see, particularly on the early projects, we see a very conservative approach to be able to demonstrate, very clearly that, yes, certainly this building will be safer than the code minimum. And so that largely explains why a lot of the early projects we see are so conservative in their design. So I'm going to just very quickly go over two projects, and I see these kind of at, as far as exposed mass timber go, they're at different ends of the spectrum, but I'd suggest they're both quite conservative designs. The first is the Brock Commons, which I'm sure most of you are familiar with. It's the very first, I would say, very tall building, mass timber building built in Canada, built in Vancouver at UBC, and designed by Action Austria Architects. Fastenep did structural, GHL did the fire safety, and RDH did the building envelope. So this was an 18-story building. First level of concrete, 17 stories of mass timber. It's a student residence, so 305 units. It had this building was constructed very quickly. In terms of actual construction, I think it was a couple floors per week. It went up, so it went up very fast. And a large part of that was this simplistic design of it, of the structure, but also the exterior wall also was able to go up as the building went up. And it was a pre-manufactured curtain wall, which was very efficient. It does have concrete exit stair and elevator shafts. And what we'll see on the next slide, this project was fully encapsulated. So the picture on the left shows the structure before gypsum board was installed. And the picture on the right depicts what the finished product looked like. And basically, there were 3 layers of 5/8 Type-X gypsum protecting the mass timber. And so what that means is that the fire rating, the 2-hour fire resistance rating that's required for this building, was fully provided for by the gypsum board. And so at that point, since the gypsum board is providing the entire fire rating, it really doesn't matter what's behind the gypsum board, whether it's a steel structure or a mass timber structure. We would never expect that mass timber to ever be involved in a fire. Because of that, this was a very conservative approach. Basically relying on the mass timber. We know that mass timber can have excellent fire resistance and whatnot, and it has inherent fire resistance. But in this particular project, they didn't rely on that at all. And the fire rating was fully provided for by the gypsum board. So this, and the reason they took this route was because they needed very quick approval if the project was going to go ahead as mass timber. I think they needed approval in a couple months. And as you can appreciate, prior to this, there were really no tall mass timber buildings in Canada. Probably the tallest one before this project was the Wood Innovation Design Center in Prince George, which was by code 6-story, but because it had a mezzanine, perhaps maybe more of a 7-story building with relatively tall stories. So previous to this project, that was the tallest. And so they had to take a relatively conservative approach to get approval in the timeline that they needed for the project to be able to move ahead as mass timber, because they needed the student residents to be ready in September for the students. So that's one end of the spectrum in terms of encapsulating the mass timber and to demonstrate compliance to the alternative solution process. And while the process on this for this project was actually a site-specific regulation, they actually amend the building code to allow for this design. Basically, the documentation and what was done for this project basically followed an alternative solution procedure. What we would expect would be submitted for an alternative solution. The next project I'll touch on is one that has building permit approval, but it has not, I don't think they've broken ground yet. This is the arbor it's George Brown College in Toronto. Moriyama Tashima Architects and Action Austria Architects are working together on this project. Fast and Epps doing structural, and we're doing the alternative solution for mass timber, and supported by GHL consultants for the other code compliance and alternative solutions not related to mass timber. So this is a relatively interesting project. It's 10 stories. It's a A2 occupancy. Switch to the next slide. So here's some renderings. As I mentioned, the building's construction hasn't started yet. But this gives you an idea of what the building will look like. So basically, it's designed to be largely exposed mass timber. But if you look at the right top photo, you'll see that in the classrooms, for acoustic purposes, they generally have quite a bit of protection on the mass timber because of drop ceilings and whatnot. So this project, we went through the design process to basically demonstrate performance is equivalent to a non-combustible building. And it went through peer review as well as part of the process to approval by the City of Toronto. Some of the mitigating features I'll just briefly touch on. So again, we took a relatively conservative approach to this building, being this was the first A2 university or academic building in Ontario at 10 stories. So one of the things that we have seen in Toronto on other mass timber projects that has set a bit of a precedent is upgrading the sprinkler system from low hazard to ordinary hazard, group 1. So basically that upgrade results in about 50% greater water delivery through the sprinkler system in the event of a fire. So this project has that. There are a number of upgrades to the sprinkler system, so that's one of them. The second is having 2 connections to the city water mains, 2 separate connections for redundancy. Similarly, there's a second fire pump for redundancy, and a second riser with valves isolating each floor. And the idea there is, again, for redundancy, and so that if one floor needs to be worked on for a retrofit, the sprinkler system for the building doesn't need to be shut down, but just that single floor can be. So those first 4 items are really targeting the reliability of the sprinkler system. We know sprinkler systems are very reliable as they are, something on the order of 90 to 95% reliable. And this is bumping that up to likely something on the order of 99% likely. As well, there's smoke detection throughout for early notification if there is a fire. The exit stair shafts and the elevator lobbies in this case are pressurized. And the fire resistance rating for the for the whole structure is based on exposed mass timber. So anywhere where we have encapsulation, the fire rating is significantly more. In many cases, because it is encapsulated with 2 layers of 1/2-inch type X gypsum, that's providing another hour. So in many cases, there's 3 hours of fire resistance on the, for the structure. And as well, we also had included a 1-hour fire resistance rating for the roof assembly, just to ensure that there's no fire spread to the roof. So these sorts of things are making for a relatively conservative design. Certainly, we can easily say from a life safety perspective that this building will be safer than what the code minimum requires. Similarly, we're also working on the academic tower, which is a project at the University of Toronto. This is a 14-story building, and I won't go through the mitigating features for this building, but they're largely similar to what we've done for George Brown, given that this is also A2 occupancy. And so it's another case where, again, we've taken a relatively conservative approach. And again, it's one of the first of its kind in Canada. So one thing I'd like to point out, and we'll see this a little bit later in the presentation too, as we look at some videos, is that mass timber does perform differently than light frame construction. And so that's why mass timber in the latest iteration of the code, it's been somewhat separated out from combustible construction, which is basically requirements for combustible construction are largely based on light frame construction. And here's an example of a CLT floor assembly with gypsum board, protected by gypsum board at the end of a fire test. So this was well after an hour into a fire test. The gypsum board had started to fall off, and the test was terminated. And this is a case where the floor assembly, this is after the fire test where the floor assembly is being lifted off the furnace. And so the picture that we're looking at right now is just as that floor assembly comes off of the furnace is on the order of close to 1,000 degrees Celsius. So a lot of heat in that furnace, a lot of radiation up at that floor assembly as it's lifted off. And so we see that the mass timber is flaming and burning. In the next photo, you'll see that as that floor is moved away from the furnace, and it's not even entirely moved away yet, but it's perhaps half of it is now to the left of the furnace. We see the flaming almost immediately goes out on the mass timber. And so the in the central portion of the floor assembly, we see that the flaming has gone out. We do see some continued flaming around the edge of the gypsum board where the heat is somewhat trapped in, and we get some re-radiation between surfaces. But this is one of the first examples we had, and this was about 11 years ago, I think, when I completed this test, where we saw that we knew that mass timber doesn't continue to burn without an external heat source, whether that's fuel contents in a compartment or whether that's other surfaces to radiate heat back. And this was a perfect example of that. And we'll see that in the photos and videos I'll show near the end of this presentation as well. So I don't have time today to go through all the various research projects that led us to this point in terms of having the building code recognize mass timber or encapsulated mass timber construction as a building type. But I will touch on just a couple of the more recent work that, that perhaps isn't reflected in the building code today, or the building code as will be published later this year, and is likely to influence the building code perhaps in the next iteration. The first is some testing that was done at Southwest Research Institute down in San Antonio, Texas. there was a number of research projects that were conducted before this that led to changes both in the National Building Code as well as the International Building Code in the US. And those research projects really, most of them, so 3 out of 4, I would say, identified that CLT, when exposed to fire, there was a phenomenon where the adhesive between layers, particularly once a layer was almost fully charred, the adhesive would allow that layer to fall off. And so what that did was it exposed fresh wood. And in some cases we saw, depending on if the conditions were right, we would see the fire die down, then the layer would fall off, and then we'd see the fire pick up again. And obviously, as we start looking at taller mass timber buildings, that's not something that we want to see. One of the things that we want to see is that the fire will die down on its own, and similar to non-combustible construction. And so a set of tests were done at Southwest looking at different adhesives, and basically developed a standard test to test the adhesives in CLT. It's a full-scale test. Let me just go to the next slide. It's a full-scale test, and it basically is testing the adhesive being used to ensure that the CLT doesn't delaminate and therefore affect the fire performance. So the next slide shows basically a floor assembly with this of CLT being tested. And this led to requirements for full-scale testing that are now in the product standard for CLT, in the 2018 product standard for CLT, and all the manufacturers in North America are now producing to this new standard. So any material that's being used, any CLT that's being used in projects are of this new adhesive type. And so these tests demonstrated that tests that meet this criteria don't delaminate and result in this adverse fire behavior. And then after this change was made to the product standard, the National Research Council undertook a number of tests with this, we'll call it second generation CLT, to look at fire performance and to see how it might be different. So at their lab in Ottawa, they were able to, they were restricted on size to be able to do the tests in the lab, but they were able to build rooms 4.5 meters by 2.4 meters by 2.7 meters high. So a relatively small room, but we know that a relatively small room makes for in this case, a relatively severe fire test because surfaces re-radiate a lot more in a small space. So CLT was used that was manufactured using the new adhesive requirements, and 5 tests were done. The first test was the CLT room with 3 layers of 1/2-inch gypsum board. And so basically we saw no contribution from the mass timber as expected. And so that creates the baseline test that we compare the rest of the tests back to understand the contribution of the mass timber. So test 2 exposed the back wall of the room and 10% of the ceiling. So basically that met the current provisions in the, or the provisions that are being added to the building code later this year. Test 3 had an exposed beam and column, or beam and 2 columns. Test 4 had an exposed ceiling with a beam and column. And test 5 had exposed ceiling and end walls. So it's test 4 that I really want to focus on here, because that is generally for perhaps 90% of projects that captures the likely scenario where we have post and beam construction or beams and columns and mass timber floors. And like I mentioned, in most of these projects, we don't have mass timber walls. And so test 4 best reflects kind of the maximum exposed mass timber we might see in a project. Here's the picture of the test setup prior to the test. So the room is right here. There's a doorway. This is the only opening into the room, and there's a vent hood that captures the fire gases. So just a plan view of the room. There's the column and a beam that extends from front wall to back wall. And these four boxes represent the wood cribs that we'll see in the next photo. So this is a photo inside the room. So you can appreciate these wood cribs make up a fairly significant fuel load in the compartment. And it works out that it's the fuel load on a per area basis is a little bit over 50th percentile for what we would expect to see in a residential building or unit. So as you can see, there's exposed ceiling, beams, and the column. And in these tests, they were able to measure the temperature in the room, and that allows us to be able to compare between the two tests. Unfortunately, at this time, they weren't able to measure the heat release rate, which is a better way to quantify the size of the fire. But these temperature measurements give us a good idea. So the graph on the left is for the fully encapsulated room. So fully clad in gypsum board, 3 layers of gypsum board. And so the mass timber doesn't play any role in that fire. So that is likely what we would expect in a non-combustible building that has gypsum board on walls and ceiling. And then the picture on the right, or the graph on the right shows the exposed column, beams, and ceiling room test. And so you'll see the temperatures, particularly after about an hour. They do continue out some time at 750 degrees Celsius for some time before dropping down out past 2 hours. It's a little bit hard to appreciate what's happening here from temperature, so I have some pictures to show what's happening in the room at different times in the next few slides. But what I want to point out here is that even in this case, this test was run for 4 hours, so 240 minutes, and the fire continued to die down on its own with no intervention from sprinkler system or fire service. So this is in that very this very unexpected and low probability scenario where for some reason the sprinklers have failed to control the fire, and for some reason, for one reason or another, the fire service hasn't been able to get to the fire and put it out. So if we look at the next few slides, this gives some idea of the fire in the room at different times. The first photo on the left is at 40 minutes. So this is while the fire is still largely fully developed. You see fires, flames are coming out the doorway. So it's ventilation controlled. Still a pretty severe fire at 40 minutes. Perhaps not dissimilar from the baseline scenario where the room is fully clad in gypsum board. You can see the wood cribs have largely collapsed, but there's still a large bed of coals that are burning on the floor. Just 15 minutes later, at 55 minutes, the bed of coals on the floor is still burning, but we see that the flaming on the mass timber has dramatically reduced. We no longer have flames coming out the door, and we just have some small amount of flaming at different parts on the mass timber. So that's at 55 minutes. Oops, sorry. At 90 minutes, so at an hour and a half, again, there's a little bit of flaming coming from the wood cribs that are left, representing the fuel load. And we do have some flaming taking place on the mass timber, small amounts of flaming. We even see some flaming in the cracks in the gypsum board. So this gypsum board was protecting CLT walls behind it. And so we do see a little bit of contribution through cracks and joints in the gypsum board, which we wouldn't normally see on a typical project because, as I mentioned, mass timber walls are not very common. And then at 130 minutes, so 2 hours and 10 minutes into the test, we see, again, there's very very little flaming left on the mass timber. There's some glowing, and we see the pile of coals on the floor from the wood crib is becoming consumed. There's very little left. So 20 minutes later, at 150 minutes or 2.5 hours, basically the fire is largely gone out. We just have a little bit of flaming at the gypsum board joints. And this is actually not from the mass timber that's exposed, but from the mass timber wall that's behind the gypsum board, where there's a little bit of charring and burning taking place. And then at 2 hours and 20 minutes, so just 20 minutes shy of 4 hours, we see that the fire has largely or pretty much gone out completely on the mass timber. And so this is what we're looking for. What we want to make sure is that the fire is not going to continue to burn and result in collapse of the structure. And so we want to make sure that the fire is going to, in that extremely unlikely scenario that the fire is not controlled by the sprinkler system or the fire service, that we're not going to see the building collapse. After this test, after this test, we cut out a section of the glulam column and measured the dimensions of the non-short portion. And it turns out after that 4-hour test that we saw charring that was pretty close to what we would design for a 2-hour standard fire resistance test, which is what a high-rise mass timber building is designed for 2 hours. So that was interesting that it lined up fairly closely with what we're designing for. So just a couple of the conclusions that came out of that research from NRC. First, it demonstrated that the CLT with the new adhesive requirements performed very well, and we didn't see any fall off of the charred wood or fire regrowth, which was expected, but good to confirm. In test 2 and 4, so remember 2 was the case where there was 10% of the ceiling and the back wall, which would meet the requirements going into the code to be published later this year, as well as for, in both cases, the fire decayed once the room contents were consumed. And then NRC concluded from these tests that the scenario with the exposed beam, column, and ceiling is unlikely to cause a significant increase in fire risk. So that was positive. As I mentioned, it's a relatively small room. It's relatively conservative from our perspective, looking at the fire dynamics. However, there's certainly a benefit to looking at larger structures. And so that brings me to some demonstration fire test work that has been going on for about a year. So this is a large project with a number of funders and partners. The funders include Natural Resources Canada, British Columbia Forestry Innovation Investment, BC Office of Mass Timber Implementation, the Ontario Ministry of Natural Resources and Forestry, Government of Alberta, National Research Council, and then partners include Canadian Wood Council, CHM Fire Consultants, and GHL Consultants. And basically, we're planning a series of demonstration tests. Some pilot scale tests were completed earlier this year in Richmond, which we'll take a look at next, as well as some full scale tests being planned for Ottawa next year, next June. And so we'll just quickly touch on those. I think these pilot scale tests will be of interest, even though they're small. It's really conveying some of these principles that I've mentioned earlier. So in the pilot scale demonstration burns in Richmond, there were 4 assemblies that were constructed. 3 of them are 10-foot by 10-foot boxes. One was light wood frame construction that without gypsum board, so basically representing a during construction scenario, fire scenario. The second box had gypsum board on the light frame walls and ceiling. And then the last one was mass timber. And really the aim of these three tests was to demonstrate how mass timber is different from light frame. So we'll look at that in the next few slides. And then the structure at the bottom was an L-shaped design. So it was basically three of these 10-foot by 10-foot boxes put together to make an L-shape. And so it was a slightly larger structure that with, again, representing the during construction scenario. So really these demonstrations were to provide some information to the concern of a fire during construction for mass timber. But as you can appreciate, some of these demonstrations, whether it's during construction for the mass timber where it's fully exposed, or if it's in a finished building where the mass timber is exposed, perhaps there's differences in ventilation, but the performance of the mass timber is quite similar. So out of these three boxes, I have a quick video I'll play, which basically shows how each of these boxes performed when we had, first of all, a garbage can fire representing a garbage can on site during construction. So this is a relatively small fire, although as far as garbage can fires go, I would say it's probably about as severe a garbage can fire as we could design in terms of ventilation and whatnot. But as you can appreciate, for the gypsum board clad room, we would expect very little damage or virtually no impact on the structure. For the mass timber, we expect the mass timber wall would be involved a little bit, but we would not expect it to spread to the ceiling. And then the light frame box, as we've all seen construction site fires on light frame buildings, we know how easily they go up. So we would expect that one to become fully involved. And so this was really an attempt to demonstrate that. Sorry for the sound, we don't need that. I'm going to skip ahead to 1 minute because it took a little bit for these for this garbage can to build up to any significant fire size. So on the left, we have the gypsum board clad room or box. On the center, we have the mass timber box. And on the right, we have the light frame box. And so just as I mentioned, we expect that nothing really happens in the gypsum board box. In the mass timber box, we expect a little bit of charring on the mass timber, but no significant fire spread. And then light frame, we would expect the box to be lost. And so as the fires grow in these garbage cans, we get to a point where the flaming is perhaps just a little bit short of the ceiling. You'll notice in the light frame on the right, as the wall starts to ignite and contribute, that flame height will continue to grow till it hits the ceiling. For the mass timber, we get a little bit of flaming on the wall, but you'll notice as that wall chars and it builds up that little bit of insulation, that the flaming largely goes out, and then it's just the flame from the garbage can, which we can kind of see now. This, just so you know, this video is sped up 6 times. That's why we see such quick fire development. But the clock on the top right reflects the actual time. So as we would expect, the light frame gets fully involved pretty quickly. It will die back, you'll see, before it takes off again a little later. The mass timber you'll see is burning a little bit, but as it chars and builds up the char layer, it will contribute less and less to the flaming. And then basically we just see a bit of paper burning off the gypsum board on the right side. So the flaming, even from a relatively severe garbage can fire up against the wall, it really is unable to climb up the CLT and reach the ceiling. on the right, we see the light frame structure fully involved. And of course, it basically continues until it collapses or is extinguished. So perhaps I'll stop this one here in the interest of time. And we'll look at the next one. So basically, because the gypsum board box and the mass timber box in those tests survived, there was another set of tests done in those same boxes with a larger fuel source, this time wood cribs. And these wood cribs are about 80 centimeters square and 70 centimeters tall. And 2 of them were placed in each box. So we'll see in each box we have those wood cribs. And you'll see that this creates quite a bit more significant fire in these compartments. So similarly, I'll play this video. I will skip ahead a little bit here, maybe. These fires do build rapidly. I think the one on the mass timber builds a bit faster. They have to reignite the one on the left to try and get it to catch up. So as the fire grows in the wood cribs, you can see it's a much more severe fire. It does involve the mass timber to a great degree. But one of the interesting things we'll see on the right as the mass timber burns and chars is that we will see that fire will die down to the point where it's really just the wood cribs burning, and the surface of the mass timber, which is now somewhat protected from a thin char layer, becomes much less flammable or contributes much less to the fire. So you'll see the wall on the back has largely stopped contributing, and the ceiling will as well as we continue. It looked very severe on the right because it is so far ahead of the gypsum board box on the left, but you'll notice that the fire severity on the left in the gypsum board box also becomes quite severe as it becomes fully involved. So you'll notice that at this point, the mass timber is really not flaming too much. A bit on the ceiling there. You'll even see that die down as the fire continues. And so again, this is the case where this would be during construction, perhaps, where there is no sprinkler system. We have whatever it is, we have quite a severe or quite a significant fuel load. But at this point, it would be very easy to apply water to that fire and extinguish it on the right in the mass timber box, as of course, similarly in the left. So I'm going to stop this here. Actually, maybe I'll just jump forward a little bit in the interest of time. So as those wood cribs collapse, you can see that the fire has largely gone out on the mass timber, as we would expect. And obviously that really differentiates it from light frame. And then lastly, I'd like to show a video from the pilot scale, or sorry, from the L-shaped box. Now this is a very severe fire. We've got 6 wood cribs in this structure. This one sped up a little bit more. It's sped up 10 times. So we'll see this one will grow very quickly. It will be very intense for a few minutes, and then it will die down on its own. So the clock, again, the clock up on the right-hand side is accurate. So there was a method in all these tests. There was a methanol pan at the base of the wood cribs to ignite. So this is you'll appreciate this is an extremely severe fire. All the surfaces are exposed and burning. So this is 6 minutes into the test. Wood cribs 6 of those wood cribs provides for a very significant fire. So already by about 7 minutes or so, the fire was going out on the floor, and now it's dying down on the ceiling at 10 minutes. the right wall is mass timber CLT, and so it is contributing at this point because of the 4 wood cribs next to the wall. So at 13 minutes, or I think at about 15 minutes, we start to see the flaming on the ceiling die down, perhaps at 14 minutes. The gypsum board on the back wall, which was steel stud, has started to fall out. And so that's also contributed to some of the heated gas escaping more readily. But again, we see that the fire dies down on its own once we get a significant char layer built up with no intervention. So again, that's pilot scale. It's showing some of the concepts that we're looking at, but we do want to also demonstrate this through large scale testing. And that's partly what we've been working on for the last year or so, is designing a set of full scale tests. You see a rough rendering of this the structure is provided on this slide, but it gives you the basic idea. This is a relatively large structure, so we want to, one of the primary objectives, maybe I'll go to the next slide. One of the primary objectives is to demonstrate excuse me, the fire dynamics in a large open office floor plan. So all of the testing really that's been done to date is looking at residential compartments, so relatively compartmentalized buildings. And so we wanted to look at, many of our projects are office buildings with open office floor plates. And so while we have a pretty good idea of how the fire is going to behave in that space, we'd like to be able to demonstrate that. So in this case, the structure on the first floor, each of these bays are 7.3 meters by 7.3 meters. So they're relatively large spans. So we have 3 bays across the front and 2 bays back. So we have a structure that's on the order of perhaps 22 meters by maybe 15 meters or so. And 2 stories. So one of the primary tests that we're looking at doing is on this open floor plate on the first story. So basically starting the fire at one end and seeing how it spreads throughout the space, and how it, in particular, what happens after the fire has consumed the fuel load that we're putting into this space. What happens, as we've seen in other tests, how does that fire decay? And of course, we want to see it decay. We don't want to see it continue to burn. So that's one of the primary tests. Another aspect of this, the tests on this structure, we're doing a series of 5 tests total. Another set of tests is in the second floor corner unit, looking at a construction site fire scenario. So the code provisions for encapsulated mass timber do allow for light wood frame partitions within the building. And so the fire code has requirements during construction that those need to be encapsulated with gypsum board fairly early on. And so from a fire safety perspective. However, we're planning on doing a test where the gypsum board is not on those light frame walls, and to look at the fire dynamics in that space. And again, we're looking to see that the fire dies down. So this test may be somewhat similar to the L-shaped cube test, only on a much larger scale and with exterior walls in place. And then the other comparison that we're looking at doing is in this bay on the left of the second story. And there's going to be 2 compartments there. And on one side will be exposed mass timber, beams, columns, ceiling. On the other side will be what the code permits in non-combustible construction. So basically a compartment that has wall linings with a flame spread of 150 and a ceiling with a flame spread of 25. And we want to compare that to the mass timber compartment with exposed mass timber, because all the testing we've done to this point has always compared back to a gypsum board clad room as a baseline, which makes sense when we're looking at trying to quantify the contribution of the mass timber on its own. But it doesn't necessarily indicate code minimum that, or the code performance that we're making a comparison to when we look at alternative solutions. And so that's really what we're looking at in that comparison test. So that's, these tests are planned for June of next year. And so we've already worked at sourcing material. We have 5 different mass timber manufacturers from across Canada that are supplying materials. So we'll have all sorts of different mass timber products. We'll have glulam, beams and columns, of course. We'll have glulam floor assembly. We'll have CLT floor assembly, of course, from different manufacturers. We'll have a dowel laminated floor assembly. And so we're going to have all these different components in the structure, and it'll be interesting to see how they all perform. So with that, I'd be happy to entertain any questions or comments. I think we have a little bit of time left, hopefully. I think I went over a little bit.
Yeah, we have one question here at the Q&A section. I'm going to read that. And if anybody else has questions, you can just raise your hand and I can unmute your mic so you can ask directly to Steve. Or you might as well, if you don't have a mic or something, you can type at the Q&A section and I will read it out loud. So the first question here is there an intumescent coating you can add to your mass timber to reach the 2 hours fire rating rather than encapsulate it in Type X drywall?
That's a great question. As far as intumescent coatings go on wood or mass timber, generally intumescent coatings are only used for flame spread. So mass timber itself generally has a relatively low flame spread rating, on the order of perhaps 45 or so. And intumescent coatings can and have been used on mass timber to reduce that down to 25. So for instance, on some projects where combustible construction was permitted, we've used intumescent coatings, for example, on mass timber in the stair exit shaft on the CLT to reduce it to 25. That works where combustible construction is permitted. But as far as using intumescence for increasing the fire resistance rating of the mass timber, there's really no products that provide a significant increase. So generally our only option for exposed mass timber to increase fire resistance is to increase the size if we don't already have it. When we have, for example, a 6-story mass timber structure, generally we have about an hour of fire resistance rating of for example, the columns, just by the very nature of their size. So they don't need to be increased for the 1 hour. But when we go to 2 hours, often we need to increase the size a little bit, depending on the size of the structure. As you can appreciate, as you get to taller and taller structures, the larger columns, as they get bigger, they'll have more and more inherent fire resistance before you have to actually increase it to meet the fire resistance rating that's required. So I hope that helps. Really, there's no intumescent coatings for increasing fire resistance at this time anyway.
Okay, any more questions? I don't see anybody raising their hands here. Oh, here, another one here. With the new code design changes, has there been considerations to limit the amount of storage during construction in these EMTC buildings?
Yeah, that's a good question. Overall, what we see on mass timber buildings is because everything is prefab, they generally tend to be very clean construction sites with very little storage material. So that's generally what we see. There are requirements that have been added to the National Fire Code, both for as the code adopted mid-rise construction, and those same have been applied to encapsulated mass timber construction, requiring things like waste bins or dumpsters having to be spaced a minimum distance from the building, and general cleanliness on site, like being kept clean and emptying waste containers and stuff daily. So there are some requirements like that, but nothing specific to storage and storage of building materials.
Do we have any more questions? Anybody can raise their hands. I can open the mic. Well, I think that would be it.
No more. I'm happy to answer any now, or if anybody has questions later that they think of, feel free to send them to me.
Yeah, for everybody, reach to Steve, or can send an email to me or David, and we will be happy to address any questions. And if we don't know the answer, we'll send to a specialist as Steve. And I hope everybody enjoyed, had a good time at this presentation. It really did. It was very interesting and very good content. And thank you very much, Steve. And thank you very much, you all, for taking your time and watching this video. Have a good afternoon, everybody, and I see you next time.
Thanks, everyone.